right there. Here's a review problem for graphs of this sort. They sometimes come in this form. When they are, you can immediately read off the shifts. It's whatever subtracted here, minus pi over 4, and whatever added over here, minus 3. That's the same thing I got by rewriting it in the standard form, a cosine bx minus c plus d, and then using the memorized shift c over b d. We call c over b the phase shift, it's horizontal, and d the vertical shift.
Can you explain again why you got the negative or minus negative pi over 2?
Oh, I rewrote it in that form because the graphing strategy applies to equations of the form y equals a cosine bx minus c plus d. When the number is subtracted in here, then the shift is c over b. We can write plus pi over 2 in here if we call the phase shift minus c over b. And some books do that. The last one we had actually used that form. I wrote it a b cosine bx plus c plus d, all pluses, and then they call the phase shift minus c over b. So you can do that if you prefer it. I'm just trying to follow the book. This book and lots of other books use a cosine bx minus c plus d. So I put it in that form, minus some number. So x plus pi, 2 times pi over 4 is plus pi over 2. I write it as minus a minus pi over 2, so I pick off c, whatever's subtracted. Maybe that was a longer answer than you wanted.
Okay, thank you so much. That helps a lot.
Sure, you're welcome. I had 3 different things I thought possibly you were answering there, questioning there, so I answered all of them. All right, so here's a shift point, minus pi over 4 minus 3. And now I know to go over to that point. Here's maybe minus pi over 4, and you don't have to scale these the same. Indeed, a lot of these graphs, the axes are so stretched that you don't want to sketch them the same, or you can't read it, right? So I'm going to go down to minus pi over 4 minus 3, and the axes are not scaled the same, but that's the shift point, right? In the xy plane. Now, the second thing I do is I discover the amplitude. A for amplitude. But the amplitude is not actually A, it's the absolute value of A. Amplitude has to be a positive number. So we say it's the absolute value of A. A is already positive, so it's 4. That helps me to draw a guideline. So the shift point tells you where to start. The midline of the wave that we drew before goes through that shift point always. And then the amplitude tells you how to draw the guidelines. So I'll say do this for the guidelines. So up the amplitude 4 units, 1, 2, 3, 4 puts you at y equals 1. So there's the amplitude 4. And then go down 4 units. The y equals minus 7. Here's the midline, y equals minus 3. And these are where the wave is going to just touch it and turn around, right? It's where the peaks and valleys are going to occur is on the guidelines. First step, find the shift point, put the midline through it. Second step, find the amplitude, go up the amplitude and down the amplitude to find the guideline. So the wave actually goes up and down by twice the amplitude, right? Now, step 3 is to find the period, which we usually denote T. Some books use T. They're both used frequently in applications. It depends on which book or which area of science or engineering you're in. P, the period is 2 pi over B. Remember the algebra things. B was the 1 over B was the stretching or shrinking factor. And so if the natural period of cosine is 2 pi, then you multiply by 1 over B to get the new period. So let's see, 2 pi over B is 2 pi over 2. This time the 2's are both numerators, so they cancel, and we get period pi. All right, so now I know something. I can go over here pi units. If this is at minus pi over 4, I go over 1 period to 3 pi over 4, right? That's 1 period later, I just take minus pi over 4 the shift point, add the period to it, and I get 3 pi over 4. Okay? And now what I can do once I have the period, change this thing. Well, let's put the last one on here though. The last thing is you flip upside down if A is negative. So flip vertically if A is negative. That turns the function upside down. So there's no vertical flip because A is
if there's something written down there, you might want to shift the camera down.
Oh, okay. You can't see the bottom? Yeah.
Yeah.
That a little better? There we go. Okay. Maybe now you can't see the top. Let's move it again. Trying to make it work. Okay. So you make a vertical flip if A is negative. Now we can sketch it once we have all that down. Since it's a cosine graph, the cosine starts at the top. Remember the natural graphs, just the basic y equals cosine, looks like this. And what we're thinking of doing is this stretching and shifting to this function. It starts at the top. So if A is positive, it will still start at the top. But if A is negative, it flips it upside down. It starts at the bottom. Here A is positive. This one is also going to start at the top, directly above the shift point. So this point is on the graph. Minus pi over 4, the same x-coordinate as the shift point. But at the top of the graph, 1. That gives you 1 point. Now, what's another point immediately, right? You go over 1 period, it has to finish a wave, so it gets back to the same y coordinate. So I'm going to also 3 pi over 4, 1 is a point on the graph. And then we said,
can you explain how you got 3 pi over 4? I'm a little confused.
Yeah. I start from the shift point. It has x coordinate minus pi over 4 and I add 1 period. The period is pi. I add minus pi over 4, the shift point x coordinate to pi the period and get 3 pi over 4. Minus a fourth plus 1 is 3/4, all times pi.
Okay, thank you so much.
Sure, yeah. Now this has a symmetry. It reaches the bottom exactly halfway in the middle here. So what I do is I just draw it that way, go all the way down to the bottom guideline and all the way back to the top, right? The sine we usually draw it by starting at the middle, go up to the top, down to the bottom, back to the middle. The cosine we usually draw 1 period by starting at the top, going down to the bottom and coming back up. So there's 1 period of the cosine the problem asks for. This is, what number was it? For your information, this is 2C if you're trying to do the homework. So there's 1 period of the cosine wave, and then if you want to graph the whole thing, of course, it's a wave that goes on in both directions forever. So it'd go like this, and just repeat that. Right. But this is the graph of this function for 1 period. Now, ideally, you want to be able to plot 5 points exactly. That's what pretty much every trigonometry book does. It says plot 5 exact points over 1 period. So here's 2 where you start and begin the period, start and end the period. Then the other one is exactly halfway in between. So you can average these 2 coordinates. You can say to get this middle coordinate here, I have to erase this board soon. I just average it, minus pi over 4 plus 3 pi over 4 all over 2. And that works. What you'll get is pi over 4. But sometimes it's better. It's pretty hard arithmetic, actually. Easy to make a mistake. Sometimes it's easier to add half the period. If the period is pi, then half the period is pi over 2. I add that to minus pi over 4, and I get to plus pi over 4. So this point right here is at pi over 4, half the period, or minus pi over 4. We'll say averaging always works, or you can add half the period to minus pi over 4. Now I know that this is an exact point on the graph. It's at pi over 4 on the bottom guideline, so it has to be pi over 4 and minus 7. Now it crosses the midline exactly halfway in between there. So you can also plot these 2 points exactly and say this is halfway between minus pi over 4 and pi over 4. Oops, I didn't draw it very well, so I'll go back and redraw it. Because it should be 0 right there, right? It should cross the guideline here at x equals 0. And this will be the coordinate 0, minus 3, the y coordinate of the guideline, and the x coordinate halfway between these two. And similarly here, this point has to be halfway between pi over 4 and 3 pi over 4. This must be the point pi over 2, right? Halfway between 1/4 and 3/4 is a half. So this is a half pi on the guideline minus 3. Here's how you get 5 exact points on the period, over one period, and make a real accurate sketch. Then on top of that, if you want, you might program it in your calculator. It will give you an approximate point, but it won't tell you these points exactly, right? It'll just tell you approximately. Any questions on that? Reasonable?
So the shift point just shows the midline of the graph. We don't use that as any like actual point to draw a line through.
It shows the midline and it shows where you should start the graph. If you're doing the cosine, you should still start either at the top or the bottom guideline with the shift point x coordinate. And actually, if you're doing the sine function, the sine will start at the shift point because it goes through the origin, the unshifted guideline function. There's y equals sine x. It's like this. It starts at 0, 0. So when you shift the sine function, you actually start graphing it at the shift point. But the cosine function, you start above or below the shift point. And it's on the line. Yeah. All right, let's see if I can erase this. Now, this red pen erases terribly. But that's how you graph any graph. A sine bx minus c plus d or a cosine bx minus c plus d. The ones that people are in. Now, there's some more to this question, actually. It also says, what is the domain and range? Remember those from algebra? These are actually really easy questions, so don't worry about these. But and they're not so important for sine and cosine, but they are very important for the upcoming trig functions. They have harder domains and ranges. The domain just means all x values for what it's defined, for which it's defined. Like if I write f of
Can
x,
you move the camera up a little bit?
yeah, that's right. I forgot to move it back. Thank you. Something like that. I've got such a small picture. Yeah. What are the domain and range of this function that we just had? Maybe I should write it again. It's 4 cosine 2 times x plus pi over 4 minus 3. Right, that was the original problem. F of x or y equals that. The domain and range of a function from algebra just the domain is all x you can put in, and y is and the range is all y that come out, all possible y. So for instance, this is an aside, I'll erase it in a second. Suppose I take the square root function. What's its domain and range? I can look at its graph and tell, right? It looks like this. It goes up forever. So the domain, I can only put in non-negative numbers, right? I can't take the square root of a negative number. It starts right here at 0. So the domain is 0 to infinity, right? You can include 0, so you write a square bracket. That means include 0. Infinity is not a real number. It's, when you write it in here, it just means go on to all real numbers. So I write a round bracket, and we say the domain of the square root function is 0 to infinity, including 0. Then we say, what's the range? Well, same thing. It starts at 0 and goes up forever, so the range is also 0 to infinity. That's all domain and range are. You look at the graph, say, what are all the x values? What are all the y values that are on the graph? And the x values are the ones for which the function's defined. That's why the domain is important, right? Where it's only defined for these values of x. Now, erase that one. How about the sine and cosine function? Well, we've already learned that you can put any number into the sine and cosine whatsoever. So the domain is actually all real numbers. So if you want on your test, you can write all real numbers x, meaning all numbers that can be written in decimal form, x. Or you can write this thing. This is what mathematicians like to use sometimes. A boldface R, or on the board, they usually write it this way, 2 bars over here. That means all real numbers also. Let's say one of those kinds of things. Or you could write minus infinity, x infinity. That's another way of writing. Any one of these three is a good answer for that one. All real numbers x, and that's true for sine and cosine. They're defined for any angle you put in. But now the range is harder. What are all the possible y values that come out? You look at the graph is the easiest way. You can figure it out without the graph by figuring the amplitude of the midline, right? Midline's at -3, and you go up or down 4, so it goes between 1 and -7 and 1, right? So that's the range, is -7 less than or equal to x, y this time. But it doesn't matter whether you use x or y, because technically it's just a set of numbers that y can be. But I like to put y anyway. So the range is all numbers from -7 to 1. That's a good answer, right? Or you can put it this way. You can put it in the interval notation, say -7, 1. Square brackets mean include the endpoints. This means the same thing as this. Or you can do interval notation if you like. You can put this. You can put a solid dot at -7. Say the number line out to 1 and put a solid dot there. If you put an open dot, it means don't include the endpoints. I'll put solid dots here. Well, any one of those three answers is good for the range. I've forgotten which one the answer key has for this, but you can use any of those notations. They're all three very popular. Use the one you learned in algebra or something. All right. Last problem on this section, then. That's sort of a review, and it shows you the other notation. But the nice thing about other notation, again, is that you can read off the shift point immediately, and it saves you a step, right? If you learn that way. I kind of feel obligated to do a little more review today since we've been out for a while. Might be one more thing. Yeah, that's it. Okay. Oh, it says find the minimum. On that last graph, mistake the min and max values. The smallest y, it means what's the smallest y and largest y? That's the minimum and maximum of a graph. It's the smallest and largest y. So the minimum was -7. That was the smallest y I ever got. And then it says, what's the x coordinate? And it occurred at, I think it was 3 pi over 4. Yeah, x equals 3 pi over 4. So that's the answer to that part of this thing we just did. You look at the point where it's at the bottom, and that's not the only point that occurs. That occurs at the bottom and infinite times, but this occurs here within the one period I sketched. So, and then it's a maximum. One, that was the top guideline. That occurred at the shift point, the phase shift point, x equals -pi over 4. So there's the answers to that part. What's the minimum? Where does it occur? What's the maximum? Where does it occur? I mean, what's the minimum maximum line? What are the corresponding x values? All right, well, now this problem, which is on the back of the homework page, I don't know if you've tried some of these or not. We didn't really get to these before. Suppose I want to take the graph and deduce the equation, right? We thought I had a graph and equation. Now, how do you equation a graph? Right? So here's the next example. I take this sketch, and I like to give these on the test, so be prepared to do this one on the next test when it comes up. It shows this sketch. And you see this point marked at -4, which is the bottom of the wave. And you see this point at the top marked at 2, which is the top of the wave. And find the amplitude, midline, period, domain, and range for this cosine function, right? And what's the equation? I'll do the hard part, find the equation for this. Except there's not just one equation. It turns out on every one of these sine and cosine graphs, so we'll say this is for the sine wave, so you know it's a sine and cosine. And by the way, sine and cosine graphs of those forms are both called sine waves. The reason being that they're both the same shape, and all you have to do is the cofunction identity proves it. Is shift one over and it lands right on top of the other one. Since they're the same shape, we'll just call them both sine waves. If we know this is a sine wave, we can make it a sine or cosine. And actually, you can make it either one because you can shift it over. So there's always dual answers like that. And on top of that, remember they're 2 pi periodic. So I shift this wave over one period, it's the same graph. Shift over another period, the same graph. I shift it this way. So there's an infinite number of answers on these. And you can give me any one you want on the test. And I have to figure out if that's one of the infinite list of graphs. All right. Now, the important point on these is to find some exact points. Marked is this point at 0.3, 0.2, excuse me. Did this earlier, I thought I couldn't read the type, and I thought it said 0.3, it's 0.2. And then there's another one marked at -4 pi over 2, exactly. So how can I find all the letters, the 4 letters, A, B, C, D, from the 5 properties that we just wrote? The amplitude, the period, phase shift, vertical shift, and whether it has a flip or not. So what we'll do is just reverse equations. We'll say first, we can do the shift point, right? Get A, B, C, D from the properties. If this is at +2 and this is at -4, then the midline has to be halfway between, right? So the midline is right there, is at y equals the average of those two. 2 plus -4 all over 2 is halfway between, is -1, right? So this is the line y equals -1 right here. That tells me immediately C over B. And then also I have a vertical shift, right, it's down 1 unit. So C over B, D are the horizontal and vertical shifts. But we notice with the horizontal shift, if we take this as our shift point, well, you can choose this one if you prefer, it doesn't matter. I'm going to take this as my shift point. Because in that case, the shift is 0, right? The horizontal shift is at x equals 0. So we'll say from the graph, choosing this as the shift point, C over B is 0, and D is how much the midline was shifted, is -1. Right? So there's the first thing. The shift point tells us what C over B is and what D is. I'm really right. Use -1, that's one of the 4 letters. I can't get C or B in general because usually I need B. In this case, then I can also find C because for the quotient to be 0, C has to be 0. But the second step is then I say the amplitude, I can just read off the graph, right? It's half the distance between the high and low point or the distance from the midline. It's down 3 and up 3, and apparently the amplitude is 3. But the amplitude is also the absolute value of A. Well, no, A is either plus or minus 3. Which is it? I try and avoid negative numbers because I'm more likely to make mistakes. But I'd like to choose this to be positive. If I choose this to be a cosine function, then it's at the top of its graph at the shift point 0. So I'm going to choose 4 cosine. I'll choose A plus 3. if I were to choose a flipped cosine with -3, then I'd have to say, well, I have to pick a shift point where it's at the bottom. So if you pick a shift point that's at the top, well, this isn't the shift point. This is the top of the graph. This is the shift point right here. Oh golly. Right here on the midline at that point. Sorry about that. 0 minus 1 is the shift point. It's at your point that you're starting in the graph, the midline. I should have said this is 0 minus 1. Somewhere I got confused along the way, didn't I? All right, so D is -1, that's correct, and C over B is 0. Okay, now amplitude is 3. If I choose cosine here, I have to go up 3 units to get to the top of the graph, and okay, A is 3. If I start with this, with the shift point at this corner, put this backwards, isn't it? This is pi over 2 -4. That's me when I do that. Sorry about that. Yeah, so this one's marked on here at pi over 2 and -4. So if I'm going to start with the shift point at x equals 0, then I'll call this a cosine because that's the top of the graph. If I started here, if I could get this one exactly and made this the shift point, then I could use a sine. And sine should go through the midline at the shift point. The cosine should start at the top of its graph, corresponding to the x coordinate of the midline. All right, so I'm going to say the amplitude is 3 for cosine, and I'm going to use cosine, so A equals +3. All right, now, once I have that, the period, I know that I can look at this thing and get the period. What's the period? I don't know this point exactly, but if I do know these two, from the top to the bottom is half the period, right? One period goes down to the bottom and back to the top. So 1/2 the period is equal to pi over 2, from 0 to pi over 2, right? Multiply by 2 and I have the period is pi. I got these 4 properties, the phase shift, the vertical shift, the amplitude, and the period. I just need one more thing. Is there a flip? And there's no flip. Since I'm choosing start at the top of the graph, I'm using cosine, there's no flip. So I want to choose A to be positive. That's what I did up here, so I can start at the top of the graph. So I essentially already encompassed this one. All right. Now I have everything I need to find all the letters, right? And C over B is 0 from this equation. And B, the period is 2. The period is also 2 pi over B. And we can from this deduce B, right? Take reciprocals and say 1 over pi over 2 pi, and multiply by 2, and you get B equals 2. Multiply this equation by 2 pi to get B. There's B by solving from the period. Then if C over B is 0 from the phase shift, that tells you that C is 0. C over 2 is 0, so C is 0. There's B, C, B, and A we already wrote was 3. Now I can write the equation. An equation for this graph is y equals A, which is 3, cosine B, which is 2, x minus C, which is 0, plus D is -1. There's an equation for this graph right here. Usually we don't like to put zeros in there, so we simplify it a little bit. We multiply this out, right? As y equals 3 cosine 2x minus 1. Not a bad idea to check the calculator. That's why I said calculator, you see if it looks like it goes through the points, right? Any questions on that one then? I can start with the equation, figure out A, B, C, D from the equation, and sketch the graph by using the 5 properties, or I can take the 5 properties, phase shift, vertical shift, amplitude, period, and flip, and deduce the equation. Now, this being said, I also said you can write an infinite number of answers. What does that mean? Cosine is 2 pi periodic, so any function of this form, y equals 3 cosine 2x plus 2k pi minus 1 has the same graph, right? If k is any integer, 0, 1, minus 1, 2, minus 2, so you multiply this by plus or minus a whole multiple of, add a whole multiple of 2 pi plus or minus. This will have the same graph because cosine always repeats. Well, any answer of this form for any integer k works. There's an infinite number. And furthermore, remember we said you could shift the sign graph over. It's possible to use the sign graph to write this also. But I'll recommend if it starts at the top using cosine, if it starts at the middle using sine, and I think it's this problem also asks you to find the domain and range. The domain of sine and cosine are always all real numbers. The range is just where the top and bottom guidelines are. It goes from y equals -4 to y equals +2. So you write this interval. The maximum is this last number of y equals 2 occurs at, well, let's see, oh, here it is, x equals 0. And infinitely more places, right? It's got period pi, so it's actually 0 plus k, right? All of them. I'll just write one of them. Minimum of the bottom guideline, y equals -4, at x equals the point halfway between pi over 2. And infinitely other points, plus k pi, where k is any integer, but I just want one to go on. Okay. There's the midline was asked for also, y equals -1, halfway between the top and bottom points. Well, the next object then is to graph the other 4 trig functions. Oh boy, right? These will go a little faster. We don't have to plot so many points, but the tangent takes pretty long. The good news is that in the long run, what's really important to be able to graph are the sine, cosine, and tangent. They're all 6 used. You need to learn them all. But sine, cosine, and tangent are used extensively, especially the sine and cosine. And the others are just occasionally. Well, let's try and graph the tangent. Y equals tangent x can be gotten as follows. Let's call it first y equals tangent theta and plot that versus theta. We can do that on the unit circle just like we did for x and y. And say, well, if the angle theta is 0, point on the graph is 1, 0. Now remember, tangent is the, let's just put tangent theta here. Tangent is y over x, is 0 over 1. Is 0. I can put the angle equals 0, then y over x is 0. Then I'll take a next special angle. You can do it in your calculator in between, of course. If I take theta equals pi over 6, now I get the point square root 3 over 2, 1/2 by dropping the perpendicular. I notice the ratio of y to x is 1/2 over square root 3 over 2. 2's cancel since they're both denominators, and I get over square root 3, or you might prefer to write square root 3 over 3. That's when the angle is pi over 6. Then I'll try the next special angle. Well, here x and y are even. They're both square root, or the same, I should say. They're both square root 2 over 2. So their quotient is 1. Pi over 4, the tangent is square root 2 over 2 over the same, is 1. We can try pi over 3, right? At pi over 3, you've got a 30, 60, 90 the other way. Now, x is a half and y is square root 3 over 2. All right, square root 3 over 2 over a half is square root 3. The 2 is canceling. Some more thing. Now you get the pi over 2. What happens at pi over 2? At this angle here, a 90-degree angle, pi over 2, you get the 0.01, and the ratio is 1 over 0. These trig functions are undefined. So at pi over 2, the tangent is undefined. How do we draw it? Because we don't. It's not a point to draw. But we want to come close to it. So how do we sketch this now? What you do is you go back and say, well, I really want to, for my applications, use x as the variable instead of theta. So once I've sketched this from the xy coordinates, I don't get confused with x. I'll just call this variable the angle x and say this is angle x versus tangent of angle x. Get the same graph, and now I can plot this in the xy plane. And the tangent looks like this. It has the point x equals 0, y equals 0, right? It has the point pi over 6, 1 over square root 3, which I think is about 0.7 or so. I should mark that. Let's write it up here. Then at pi over 4, y is equal to 1. So it's here. Then at pi over 3, it's got the value square root of 3, which is about 1.7. So pi over 3, or root 3 is a point on here. And at pi over 2, there's no value. I'm just going to draw this vertical line here. And the calculator can fill in dots between. It's a nice smooth curve that runs through these points. But what does it do from here to here? I drew a dotted line actually anticipating this. This turns out to be an asymptote. If you think about it, you can verify it as follows. Take an angle that's real close to 90 degrees, real close to pi over 2, like this. Then the y coordinate is going to be really close to 1, like 0.99 or something, when x is 0.01. So if I just go an angle, I only come over 0.01. Maybe this is 0.99 approximately, and this is 0.01. Then 0.99 over 0.01 is about 99, right? This graph, when the angle puts me here, is about 99 or 100. If I make a triangle even skinnier, so its base is only 0.0001 wide, and the top is still about 1, then the ratio of y to x is about 1 over 0.001 is about 10,000. And you start to realize that by making this triangle skinny enough, I can make the ratio of y to x as big as I want. So what happens is, I'll put dot, dot, dot here, say pi over 2 is undefined. But you want this to go up and up and up through all real numbers because you can make this tangent as big as you want by picking a real close angle to 90 degrees, pi over 2. That's all the points I'm going to plot because I want to illustrate some other things that come out of this. Once you have that, you've got everything, right? Because 1, you plot points. 2, you can use some properties here. Another property is that tangent x is odd, right? What does that mean? It means if I've got these points here, they've got corresponding sister points over here with another asymptote over here, the same distance. In other words, remember, odd functions are symmetric through the origin. Told you these even odd properties would be useful to us. This point here, pi over 6, 1 over square root of 3, has a sister point over here, minus pi over 6, minus 1 over square root of 3. right? Minus both coordinates. So that it's symmetric through the origin. Pi over 4, 1 has a corresponding point here, minus pi over 4, minus 1. And every point does. This other one has one here. And it's exact duplicate graphs. If you take this graph over here, flip it over this way, and then flip it down, you'll exactly land on this one. That's what an odd function does. It flips through the origin like that. So there's the graph of tangent. And now finally, we can graph the whole rest of it from here, actually. Because tangent of x has period pi. We call it pi periodic is the other way of saying it. Unlike sine and cosine, their periods are 2 pi, right? This has period pi. And here's how you can see it. I'm not going to do all the details. It's not worth it. What you want to have is a feeling that when you start to forget, is it 2 pi or pi periodic? You can kind of visualize this and figure it out. That's where mathematics has a nice advantage over some other things. Like in foreign language, isn't it a big advantage if you already knew your Latin or something? Then the words sometimes sound like the Latin. You can kind of guess what the translation is supposed to be in French or Spanish or something that's Latin, that derived from Latin maybe a long time ago. And you can kind of guess what the word's supposed to be. Similarly here, when you remember the unit circle, even if you don't remember all the details of the proof, you can kind of guess what the result is going to be. Here's how you can see in this pi periodic. That's why I do these proofs, to memorize these things longer and have an understanding for what's going on. If I have any angle theta, let's put it in the first quadrant just for simplicity, but it works anywhere. I have a coordinate point x and y, and you remember those are supposed to be the cosine and sine, right? This is cosine theta, sine theta. What if I take the angle directly opposite? Directly opposite has to go through the point minus x minus y, right? And directly opposite angle, I add pi to this. What I can then infer from this diagram, I need some space here, maybe on the bottom again. Let's get rid of this. Is that for any angle theta, right? You always put an opposite angle. Tangent theta is y over x. That's its definition of the unit circle. Is also minus y over minus x by algebra. The minus is canceled. But minus y over minus x is the tangent by definition of this angle, theta plus pi, right? Theta and pi more. That's it. Tangent repeats every pi units. Any tangent of an angle theta is equal to tangent of theta plus pi more, right? Or you can minus pi if you do it this way. It doesn't matter. So that shows that tangent has period pi, and that tells us actually how to draw the whole graph now. Because you take this thing that goes between minus 2 and pi over 2 and pi over 2, that's length pi. That's one period that I drew. So all I have to do is repeat this image over and over and over, and I've got the whole tangent graph. I simply take this and draw the same graph here. These asymptotes are pi apart. The next asymptotes will be pi apart. This will be at minus 3 pi over 2, for instance. If I go pi over this way, I'll be at plus 3 pi. So every pi unit pi units, the crossing point repeats. So if this is 0, 0, this point here is pi 0. We just move over pi units. This point here is minus pi 0. There's the graph of the whole tangent function. It goes on forever, but it's not a wave. It's this thing that goes between plus and minus infinity. And it's not defined in every odd multiple of pi over 2, you notice. There's the graph of y equals tangent x. And now what can you do? Graphs that people tend to need in industry and other applications in sciences and so forth, by stretching and shifting this one, just like we did with sine and cosine. And these are going to get faster and faster because the next 3 graphs are motivated quicker. This one, the odd property and the pi periodic property. And we'll say this now to sketch the graph of y equals the same kind of thing we do with sine and cosine. A tangent bx minus c plus d. What do? You do the same algebra principles that you did with sine and cosine. All right. A is just a vertical stretch about the x-axis. You stretch it by a factor absolute value of A and turn it upside down if A is negative. All right. 1 over B is the horizontal stretch, just like with sine and cosine. So that will tell you the new period. And C over B and D are, again, the coordinates of the shift point. We don't call it a phase shift anymore because it's not a wave, but we'll just call it a horizontal shift. And I won't call A the amplitude anymore because it's not a wave, but I'll say it's the vertical stretch factor. So what we do is we write the same things with a little different notation. And then there is one change because tangent is pi periodic. The new period, instead of being 2 pi over b, is only pi over b. Right? You take its natural period and the stretching factor 1 over b and get pi over b. So let's write it out. 1, you say that it has vertical stretch instead of amplitude. Vertical stretch, absolute value of A. You say that it has period, the natural period of tangent divided by b, pi over b. This assumes b is positive. We said before that on all these graphs, if b is negative, you should immediately use their even or odd property, either get rid of it or take the minus out and put it on A, so that once you actually go to graph it, b is never negative, then all these properties apply. If b is allowed to be negative, then you put absolute value in here and flip the thing. So we'll avoid all that kind of headache. It's already hard enough to flip it vertically. All right, so that's a vertical stretch of A, a period, and then there's a shift. It's the same thing, right? We do the same things to this function, and it applies to all functions. We'll say that the shift point is again C over B D. I kind of like to do this one first. I listed it third on this list, but I think this should go at the top, really. Do it first when you do your graph. Do the shift point and then the stretches. And then finally, there's a vertical flip if A is less than 0, because it makes all the y coordinates negative that were positive, all the ones that were negative positive. And that's it. It's the same 4 things. It's just the period is pi over b instead of 2 pi over b. Let's see if we can do one of these examples. By the way, I showed you my graph. It's always sketchy. Let's see what a real graph looks like. I wanted to show you one of these times, and I've got it here for you now. That your textbook is a really nice free textbook, but there are other nice free textbooks these days. They're becoming very popular. Yours is the top of the line textbook from OpenStax, a major textbook publisher for free textbooks online. And then you can pay something to get a hardbound version if you want. It's only like $20 or something. But when I share my screen here, hopefully you can see this. Here we go. Here is the LibreText. It's another online resource. If you don't like the reading of your text, this is free. Just download it and look at this one, right? Plus, there's lots of them at the library. Trigonometry does not change that much. If you don't go back more than 50 years or so, all the notation is the same. Everything works the same. It's not like you're doing advanced research math and it changes, right? So trigonometry books of all sorts. You may have one around the house from somebody who took it before at work. This is a nice online version you can put on your laptop. And so here's showing the unit circle and the cosine and the sine and how you can, just like we've been saying, at angle pi over 6, here's the y coordinate, angle pi over 3, here's the y coordinate, and angle pi over 2, here's the y coordinate 1, and then they start coming down. And it shows you how to sketch this nicely from some other authors. And now you can see here's the whole sine wave, 1 period, 0 to 2 pi. Isn't that a nice graph? Better than mine on the board, right? There's the whole graph of sine x goes on forever. Here's the cosine x. You can see these look the same shape, just shifted over. It proves that they land on top of each other. If you just move this one over pi over 2, 90 degrees to the right, and it lands on sine. Here's the tangent. This is what I really wanted to show you. You notice it has asymptotes at odd multiples of pi over 2. That's worth writing down. And crosses the x-axis at whole multiples of pi. Right? And it has these useful points. At pi over 4, it's 1, and at minus pi over 4, it's minus 1, we proved, right? And so there's the nice graph of that. Maybe I should write that up on the board just to be complete here. And it has no minimum or maximum, right? Because it goes up forever and down forever. There's not a largest or smallest coordinate it takes on. Here's some of the other ones that are coming over. Coming up. I just thought you might like it. Here's the cosecant function. There's a really neat way to graph it that we're going to do. If you just take the sine function, here's the sine. Its reciprocal just looks like this, where sine is 1, its reciprocal is 1, right? Because 1 over 1 is 1. Or sine is a half over here, about here. The cosecant is 2, where sine is real close to 0. The cosecant 1 over that number is real large, and so it approaches an asymptote here. And so there's a graph of cosecant. We'll talk about that more shortly. And here's the graph of secant. And so these books have nice pictures, and some of them are better than others and more understandable than others. Maybe you want to take a look at some of these other texts, like the Libre text. One of the MIT guys I have had vague acquaintance with is involved in this project, actually. So I'm maybe prejudiced in favor of the Libre books. But here's the cotangent function also. It looks like the tangent function turned upside down and shifted over. And what I want to point out when I do the cotangent function is actually they're the same shape. The tangent and the cotangent are exactly the same shape. If you flip the tangent upside down and slide it over 90 degrees, pi over 2 radians, excuse me, you'll see they land right on each other too. And also the secant and cosecant, maybe you noticed, are exactly the same shape. You just need to shift them over. So it's not so hard to graph these. Their sine and cosine have the same shape. Tangent, cotangent have the same shape. Secant and cosecant have the same shape. You just need to be able to flip and shift these things to land them on each other. All right, let's stop sharing the screen and see if I can do a problem so I don't blab all day here. Now hopefully you can see me again. Let's try graphing a tangent function using the same graphing pi over b instead of 2 pi over b. And here's an example. Sketch the graph of this tangent function, y equals, actually, let's do this one. 2 tangent pi over 4x minus pi over 8, just like that. How can I sketch the graph? Those are the 4 steps. I'm going to do the shift point first. And I'll say the letters evidently, just by reading, are A is the number that multiplies tangent, B is the number that multiplies x, C is the number that's subtracted from bx, and then D is whatever's added on the end. Well, there's nothing there, so I put a plus 0 and say D is 0. Right? All right, so now I have all the letters. I can figure out all these properties, right? The shift point, the phase shift, if it was sine, this is now just the horizontal shift, is C over B D, just like before. You don't have any new memorization to do for these, right? C is what's subtracted here, so it's plus pi over 8. Over B is pi over 4. Yes, man, well, the pi's cancel, and I get 4/8. You take top times bottom over middle times middle, is 1/2. Interesting, this one has a period that doesn't have pi in it. That happens whenever B has pi in it. If B has a pi in it, then your period will just be without a pi in it. Your shift point, excuse me, will be without a pi in it. So I'm going to just shift it 1/2 unit. And then, oh boy, that was just the C over B. And then D was 0. And so the shift point is 1/2 0. And I'm going to go start at that point, right? The shift point is really important for sine and tangent because the graph goes through that shift point, right? The graph of the untranslated function goes through the origin. The graph of the translated function always goes through the shift point. right? The origin shifts to that point. All the others shift and then are stretched. So I can start graphing this now. I hope you can still see the board. It's a little hard to erase it right now. I'll go over to the point 1/2 0 right here. By the way, you notice there's no vertical shift, right? The horizontal shift is 1/2, the vertical shift is 0. This is common in applications of everything but sine and cosine. Sine and cosine, you may have the water waves way up here and you want to give a vertical shift, but tangent, cotangent, secant, and cosecant, most applications don't need the vertical shift. So usually I leave it off on the examples for that reason. It's not that you can't have it, you certainly can, right? So the shift point here is 1/2 0. Now here's how to graph the tangent. Instead of drawing like the sine where you drew the shift point and then you went up and down to the guidelines and drew them so you know where the top crests and bottoms of the waves were. Instead, we're going to go over half a period each side and sketch the asymptotes. So instead of sketching guidelines, we sketch asymptotes, and we need the period for that. Let's see. The second point here is the vertical stretch, replacing amplitude, is absolute value of A. Amplitude was vertical stretch also. We just like to call it amplitude since it's a wave. So the vertical stretch is absolute value of A is 2. Every point is pulled twice as far away from the midline of this thing, from the shift point here. And now the period, since it's a tangent, is not 2 pi over b, but pi over b is pi over 4. Again, you have to be careful of these, right? Pi is pi over 1, all over pi over 4. Oh, I'm going on the bottom again. Let's move this down a bit. That's okay. I hope. So it's pi over 1 over pi over 4. The pi's cancel since they're both numerators. It's just top times bottom over middle times middle. Is 4 pi over pi is 4. Right? So the period is going to be a number that's 4. When B has a pi in it, both the phase shift and the period tend to come out to be numbers. So this will be a period of 4. That means that in order to sketch this, I go half the period on each side from the shift point. I'll go over here from 1/2, 2 units, half the period. 1/2 the period equals 2. And that will not be another point in the graph, but an asymptote half the period over. And this is, if it's 2 units over, this must be 5 halves, right? 1/2 plus 2 is 5 halves. Now I go 2 units over this way to minus 3 halves, right? 1/2 minus 2 is minus 3 halves. And I sketch this asymptote here. And now I know exactly how to draw this, right? If it's not flipped, and this one's not, that's the last point I need to write. Since A is positive, it's unflipped. A is bigger than 0. But the tangent function always just goes up like this towards this asymptote and down like this towards this asymptote. Right? That's it. There's a nice graph. I might give you full credit for it just like that, maybe. If the tangent is flipped, if A is negative, then you just draw it down like this. You turn it upside down and draw it down this way. That's the only difference. Right? But now there's this question of, well, maybe I should have drawn it flatter or steeper. How do I know? The one thing we haven't taken into account here. What is the vertical stretch? Well, I go halfway between these. Halfway between 1/2 and 5 halves is 3 halves. And I remember the original tangent graph. On the original tangent, here's pi over 2 where the asymptote is. Halfway between at pi over 4, you remember the tangent is equal to 1, right? So the point halfway in between is 1 unit above this central point right here, which has been shifted to here. So this should be 1 unit up if it's not stretched. But the stretch factor is 2, so I make this 2 units up. Whatever the stretch factor is, that's how far you move up from this shift point. And then similarly on the other side, if you go half a period over to minus 1/2, this should be down at minus 2. I don't expect this to be a perfect graph, but I'd like to see one coordinate on here to tell if it's about the right steepness. And this is the easiest one. Just go halfway between the shift point and the asymptote, up the stretch factor to this point, and down the stretch factor to this point. Right? That's it. Any questions on all that one? It's pretty complicated. But what happens is when you do enough of these, you start to be able to picture it in your mind without even drawing it down. And if you have an idea what you're thinking about, you can often deduce a lot of properties of the result. You know, right? Okay, like it's period immediately, then oh, it repeats after this number of periods, we'll get the same thing. And then the whole tangent function is myself enough around this whole board. Right? But it repeats over and over. So what happens is if the period is period was 4, I move over 4 units from a half and get 4.5. That's 9 halves. I cross the middle again. I draw exactly the same graph in exactly the same way. The asymptote repeats every 4 units also, right? So if this is 5 halves, that's 2.5. I move over 4, that's 6.5. What's that, 13 halves? So 5. So I just repeat this over and over. The period is 4, so I go 4 more and 4 more and 4 more. And I just keep drawing forever. So this goes on, and I can plot these exact points. This one, 4 over, halfway between 9 halves and 13 halves is 11 halves. This should be also at 2. And so you can draw a nice graph like that for tangent. Okay. That'll do that one then. One example really pretty much does it. What you have to do after this is practice it. If you do want another example, we can do one. Maybe you'll want one at the beginning next time. For instance, ask me questions at the beginning. That's when you usually learn the most, is that I can figure out what's hard. Right? That'll also help on my lecture that follows that. So the thing about questions, bring them at the beginning is a good idea. That's what we're meeting for instead of just doing a book. But, how about the cotangent? We won't have time to do the stretching and shifting, but the fact is that all the rest of these things stretch and shift exactly the same way. It's just a cotangent bx minus c plus d. And you take the cotangent graph that we're about to develop and shift and stretch it, right? So to sketch y equals cotangent x and the shift and stretch it version, we can actually do this one really quick. Think of this. Remember the cofunction identity? I can use the cotangent of x is tangent of 90 degrees minus x, or radians pi over 2 minus x, right? That's the cofunction identity. That tells me how to graph the whole thing. Because now our stretching and shifting techniques tell us how to graph this, right? Tangent is an odd function, so I can pull the minus out and say this is minus the negative of this angle, x minus pi over 2, right? This is minus this one. And I pull the minus out. So the tangent, I can make this angle minus if I pull the minus out to cancel it. Because tangent is odd. Now, how do I sketch this one? It's easy, right? A equals -1. See, I stuck in another graph of tangent. What multiplies x? 1, so b is 1. C, the subtraction here is pi over 2, right? Whatever subtracted is the shift. And there's nothing added on the end, so it's 0. All I have to do is know a tangent graph, and I have cotangent, because the cotangent graph is this tangent graph, tangent of x minus the tangent of x minus pi over 2. So now what I do is I go to the shift point, c over bd is pi over 2 over 1 is pi over 2, 0, right? So I'm going to go over this point here, pi over 2, 0. That's the shift point for this tangent function. A is negative, right? So it's flipped upside down. Let's do all the other things. The amplitude, the absolute value of A is +1, right? Amplitude is always positive. A can be negative, but the amplitude is absolute value of A is positive. The period of tangent is pi over b, is pi over 1 is pi. And so this has the same period. I can, and just like I sketched tangent before, I can go half the period to the left. The period is pi, I go pi over 2 to the left, and there's my asymptote, x equals 0, and I go pi over 2 to the right, half the period, at x equals pi. There's my asymptotes. And I draw it up through here. Oops, except flipped upside down, right? So it's flipped since a is less than 0. Instead of going up through this point, I go down through the point. There it is. There's the graph of y equals minus tangent x minus pi over 2. Quickly using our graphing things. You can figure this out in your head sometimes. And we can say, well, the stretching factor's absolute value of a is 1. So this point halfway between at pi over 4 must be a 1. It's not stretched at all. And this point at 3 pi over 4 is also not stretched at all. It must be at minus 1. And there are 4 points on this graph, and then tangent repeats every pi units here. All right. Wait a minute, I just sketched tangent of x minus pi over 2. It has the same graph as cotangent x. This is the graph of cotangent x. And now you see it's the tangent function flipped upside down and shifted over pi over 2 units. Next time, we'll do graphs of cotangent, secant, and cosecant. Any last second questions? On 6.1, if you haven't already done this, look at 1 through 6, all but the last problem. To do. And then on 6.2, we've only done the cotangent, so the tangent really, so we haven't done much. You could do 2a, right? So 6.2, try 2a, but I'll assign pretty much all the problems out of 6.2 next time. Those are ones to get you ready for next class. Thank you for coming in. Come see me in my office hours coming up in 15 minutes if you have questions, right? Thank you.
Thank you. Have a good day.
Yeah, you too. Thanks.